Hello everyone, welcome to this online course on material science. This is lecture 18 in the module 1 on magnetism. In this lecture, my plan is to give you a self-contained introduction on electrons' spin angular momentum denoted by S vector hat, right? So that's the spin angular momentum of an electron. And how do we model this operator in quantum mechanics, right? Let me first give you three important matrices to understand this operator. Those matrices are usually known as the Pauli spin matrix. And we have three of them. The first one is the sigma x. So these are 2 by 2 traceless matrices. So that's sigma x. We have another one is sigma 2, which is 2 by 2, and this is 0 minus I 0, and as a sigma z we have 1 minus 1 0 0, right? So these are three 2 by 2 Pauli spin matrices. So we can form a spin operator, right? A spin vector operator, but from these three matrices. So this sigma operator will have three components: sigma x, sigma y, and sigma z, right? And if I write it out in Cartesian coordinate system, so we have ix along the unit vector, which is sigma x, and then we have jy unit vector, then sigma y, and then that's a kz unit vector times sigma z, right? And the reason that I'm introducing these matrices is that the spin operator, right? The spin angular momentum operator, to be more precise, of the electron is defined as the h bar by 2 times the Pauli spin matrices, right? And then you can see that this spin operator has three components also. Let's say we have some Sx, then Sy, and Sz, right? And if you write this sigma in terms of the sigma x, sigma y, and sigma z, you can easily see the x component, which is an operator, right, of the spin operator, right, is nothing but h by 2 sigma x, right? And the y component of the spin operator is h by 2 sigma y, and the z component of the spin operator is h by 2 sigma z, right? That's why this Pauli spin matrices are very important, because they kind of specify the spin operator of the electron, right? And we know the matrix notation of sigma x, sigma y, and sigma z, they are just 2 by 2 traceless matrix. So now we really can write down what sigma x is. So this is 0 1 1 0, right? That means the x component of the spin angular momentum operator is also a 2 by 2 matrix, right? And what about this Sy? The same story. We have another 2 by 2 operator, 2 by 2 matrix here. This is 0 minus I and I 0, right? So another 2 by 2 matrix. And also the z component of this spin operator is also a 2 by 2 matrix, right? That's an important observation for the spin of the electron. So once we have these components, then I want to give you the commutational relation between them, right? Let me specify Sx, Sy, how the individual components of the spin operator commutes or not. So let me write down the required quantities first. So that's Sz, Sx, right? And these are I times h. So we have Sx, Sy, this one is Sz, right? And every one of them are operators. We have Sy, Sz, and on the right hand side we have IH bar times SX, right? So you can see a cyclic pattern. So ZX, it should be a Y, right? So none of the spin components of the spin angular momentum of the electron commutes with each other, right? That's the central message. That's why you cannot have a common set of eigenstate of any of these operators, right? That's the central point you should have. It's like the orbital angular momentum, same. The individual components do not commute with each other. Then what we did with the angular momentum is the same here. We need to form an operator which is the S square operator, right? It means we need to perform the dot product between two spin angular momentum, and this is nothing but Sx square plus Sy square plus Sz square, right? And all of them are operators. Now the interesting thing is that this S square operator commutes with every component of the spin operator, right? That's 0 for I is equal to X or Y or Z. What that implies is that these two operators can be simultaneously possess a set of common eigenstate, right? So we need to define a common eigenstate for S square and Si, and always the case, which I should I pick? Is it the X, Y, and Z? I told you in magnetic problem, we usually say the Z-axis is the axis of applied magnetic field. So usually we always consider the Z component of the spin angular momentum, right? So that's our starting point. Now the question is, what is the common eigenstate of these two operators as they are commuting with each other? The way you denote this state or the kth by two levels, right? One is S and then the second one is Ms. This S is the quantum number associated with the total spin angular momentum of the electron, and this is the quantum number associated with the Z component of the spin angular momentum, right? Now the question is, we need to know how this operator operates on this eigenstate, right? So let's see. Sorry, that should be an S square. This is nothing but small s, s plus 1, h square times the same state, because that's an eigenstate, right? And that's the eigenvalue. So this SMS state is an eigenstate of S square operator with the eigenvalue s plus 1 h square. That's the eigenvalue, right? And the Sz operator, when operates on this state, will give you this number ms times h bar times the same state, right? So from these two definitions, you can see that SMS is a common eigenstate for S square and S, but for S square, the state has eigenvalue s plus 1 h square, and for Sz, the eigenvalue is ms times h, right? And the range of this ms is another important point to remember, is that the ms quantum number will always lie between minus s and the plus s. And the important thing is to remember that for a single electron, this s quantum number is always plus half. What that means is that ms lies between minus half and plus half, right? Always. But the thing is that ms has to be in the steps of unity, right? So there are only two possible values, because the range is from -1 to +1. So ms can be always, right? When s is half for always a single electron, ms can be either plus half or it could be minus half. So this things is fixed for a single electron. You have to remember this. This will have important consequences in the different calculations as we will go. We will see as we go along, right? So how do we write this state now? For example, let's say the kth should be S and then ms, right? So what is the possibility here? S is always plus half. You cannot change it for an electron. Ms could be either plus half, so that's one state. And the other state is S could be half and ms could be minus half, right? This state usually denoted by spin up in different textbook, and this state usually denoted by spin down. It's easier to write, right? In this way it's a kth, but pointing down an arrow, and this is the pointing up, an arrow is pointing up in the label, right? And also you will see in some textbook this downwards arrow also sometimes denoted by this minus sign, which is means spin down, and this one by a plus sign, right? And this ms is nothing but the quantum number associated with the sz, remember, right? The z. So z is the z component of the spin angular momentum of the electron. Now let's try to understand that what are these values of the eigenvalue, right? So let me find out what this state is. So I am operating in a spin up state with the sz, and what it should give me, it should be ms times h times the up state, right? And what's the ms? It's in the up state, it's plus half, right? Similarly, when sz operate on the down state, spin down, it will give you the same msh down, right? Because these are the eigenstates of the sz operator. But now in the down state, what is the value of ms? That's minus half. So that should be minus h by 2 down, right? And what about the s square now, right? These are operators. So let me just put hat for consistency. So now what about this s square operating on plus? You know what is the eigenvalue, right? The eigenvalue is s plus 1 h square, right? That is the eigenvalue times the state itself. And what is the value of s for single electron? Always half. So you can see that we have a half plus 1 h square, right? And then the state up. So what's that? We have 3 by 4, right? That's the half, that's the 3 by 2. So we have 3 by 4 h square on up, right? So what do you say? You say s square operates on the state up. It will give you an eigenvalue 3 by 4 h bar square times the same state, right? And similarly, when s square operates on the down state, right? So it will give you the same value s into s plus 1 h square times the down, right? But the s is always the same, whether it's up or down, the result is the same, right? 3 by 4 h square times the down state, right? And you remember, this down state has s half and ms minus half. But the ms doesn't appear in the s square operation, right? So it doesn't matter which ms we are talking about. Okay, now let me show you how do you usually find out the expectation value of these operators, right? So you will see in different occasions you will be asked to calculate quantities like sz. So you need to find out the expectation value of the sz operator, right? And how do you do that? And you need to ask yourself, what are the bras on the kths, right? So let's say we have ms bra and then sz, then sms, right? That's the expectation value. And you know what sz produces when hits operates on sms. So this part will give you ms times h times the same state, right? That's just a number, you can bring it out. The logic is the same, ms by h is ms bra inner product with sms skate. So this is inner product is 1, right? So we have ms times h. That's how we calculate the expectation value of SZ operator, right? And depending on ms could be plus half and minus half. This value could be plus h by 2 or minus h by 2, right? And also it could be possible that you are asked to calculate this expectation value not between the same state but two different states, right? Then how do you do that? Let's say I'm trying to calculate the expectation value of the SZ operator in two different states, SMS and S prime MS prime, right? Then you know what this part will give you. So that's the same, and then this will give you MS H bar times the same state. That's just a number. You can bring it out, and the inner product, right, between two different states. But you know, to get a non-zero value, S prime has to be equal to S and MS prime should be equal to MS. And how do you enforce that condition? You say that Kronecker delta S prime has to be equal to S and MS prime has to be equal to MS, right? That's the expectation value of this operator. Similarly, you will be asked to calculate like the S square expectation value, right? And how do you calculate that one? You know the state. Let's say first we are calculating between the same state SMS, then the operator itself times SMS, right? So you know what this operator, when operates on SMS, will produce. So the bra will remain the same, but here it will produce S into S plus 1 times H square times the same state, right? But that's just a number. Bring it out, cite the bracket notation, and what we left is the inner product between same state, right? SMS and SMS, that's 1. So expectation value is S plus 1 H square, right? So we have some 1. And also you can do the same analysis between two different states, right? Let's say if this were some primed state, then this will be also a primed. So everything will be remain the same, but this one will be a prime. Then we need to put some extra condition of the orthonormality that S prime has to be equal to S and delta MS prime has to be equal to MS, right? So those are the same calculation, but I'm just showing you that you will understand how do you perform these manipulations. Okay, and similar, you remember in the in the orbital angular momentum discussion, I have mentioned two operators, like ladder operators. Do you remember L plus and L minus? So similarly, for the spin angular momentum, let's define the spin ladder first, right? We have a ladder for sure because the spin, so we are writing SMS, right? Always in this configuration. So S could be plus half and MS could be plus half, or S could be half, MS could be minus half, right? So that's our two-step ladder. That's only the two steps. So there should be some operator where we can, with the help of those operators, we should be able to make a transition from this state to this state and this state to this state, right? So, and that's what this S plus operator is. So this will help you to go from this state upwards to this state. And the way you define this action of this operator is that when S plus operate on this SMS state, the state will be changed, right? Because you are making a transition from MS to MS plus 1 state, right? The MS value will be increased by 1, but now the value associated with this state will be S minus MS times, here we have S plus ms plus 1, right? And similarly for the minus operator, the ladder operator, it will help you to decrease the ms by steps of unity, right? So then here we have minus plus 1, right? Quite similar to with the angular momentum operator, right? And so here ms will be decreased by 1, and that's your value, and we have a square root similar to this one. Now if you are already in this state and you want to go below, you will understand there is no state below for a spin half particle, right? That's why when you in this state, if you operate by S minus, it will produce a 0, and when you are in this state and if you want to go above this state, you cannot, because there is no state above. So if you operate S plus on this state, this will produce a 0 too, right? And usually the way we denote these things is that when S plus is operating on a state where ms is already in the highest S state, this will be a 0, right? And also when S minus, you want to operate a state where ms is at the lowest in the range, which is the minus half state, that will give you also a 0, right? So you cannot go below this ladder. So ladder ends here and here, and you can only make transition in between these two. Okay, and then similarly you can ask that, okay, can we have this operator, and how do we find the expectation values of this operator, right? Let's find the expectation value. Let's say you want to find out the expectation value of SZ, and you know what the state is SMS, let's say, and let's say it's a prime state, and then we have some S plus, and here we have SMS, right? You know what S plus does on SMS. Let me write it down. So S plus will give you H times S minus ms times S plus ms plus 1 square root, and then the state itself, right? And state is changed, sorry, by where ms is increased by step 1, right? So that's just a number, and you can bring the number out. We have S minus ms, S plus ms plus 1, and then the inner product between S ms prime, S ms plus 1, right? And then you know the orthonormality condition dictates that this index, pairwise index, has to be equal for non-zero contribution. So just copy this term here, and this will be ensured by 2 Kronecker delta, saying that S prime has to be equal to S and ms prime has to be equal to ms plus 1, right? Otherwise this inner product is 0. So that's the expectation value of this one. And similarly, I believe you will be able to perform the minus 1 too. So if this is a minus, here it will be a minus, then we will have plus here and the minus here, right? And then this will be a plus, then this will be a minus, right? And everything else will be the same. So that's easy. And the one where you want to calculate the transition. So now I want to give you the last bit of rules, just in case you need them, is that we know what SZ, right, is giving us when we operate on this state, right? We define this with this relation, let's say SZ on up, SZ on down, so we know what SZ does. But one may ask the same question here, is that, okay, we also have other operators, right, like XX and SY. Just to give you some idea what this operator does on the up or down state, right? So let's say we want to understand what SX will give us when operates on an up state, right? An up state means S is plus half, ms is plus half, right? So now remember what Sx is. Sx is nothing but sigma x, right? And what this state is state up. And let me tell you, one rule is that this up state also can be denoted by a column vector with one row and 2 rows and 1 column, right? That's an equivalent representation. Remember that for up state. And we know why we are using this representation, because we know the matrix equivalent of sigma x. Do you remember that? The sigma x is nothing but some 2 by 2 matrix element, right? Let's write it down here for our convenience. So h by 2, and the sigma x is 0, 1, 1, 0, and then we have this 1, 0 state, right? And you can perform this matrix multiplication, right? So 0 times 1, 1 times 0, 1 times 1, 0 times 0. So this will give you h by 2, 0, 1, right? So 1, 0 is denoted by spin up, and this 0, 1 is nothing but spin down. Just remember, this is as a rule. So what this Sx operator is doing is that it flips the spin, right? It flips the spin up to down. And similarly, you can show that when Sx is operating on this state, right? So we have h by 2 sigma x, and this down is represented by 0, 1, right? And you remember what 1 is. From that calculation, you just represent sigma x with this unit vector, and you can show that when you do the matrix multiplication, this is nothing but h by 2, 1, 0. And what is this 1, 0? This is as though h by 2 spin up, right? So also Sx is flipping the spin down to up. Similarly, you have Sy, right? Convince yourself, do this calculation. It's very easy, right? Let me just sketch the picture for you. I want to calculate this bit. So we know what is this, h by 2 sigma y. That's this operator, and this up is nothing but 1 by 0 column vector. So what is the representation of y? Y is nothing but h by 2, 0 minus I plus I 0, and here I have 1 times 0, right? Perform this calculation, you will see the matrix multiplication will give you minus, and then, this will give you I times h by 2, right? 0 times 1. What is 0 times 1? That's your spin down state, right? So also Sy is flipping the spin, but now with the value IH by 2. And here we have h by 2. Similarly, you may want to know what Sy will do when operating on down, right? Down state. Let me give you the answer, and you should convince yourself that this is nothing but minus IH by 2 spin up. So the punchline is that these Sx and Sy operators can flip the spins, right? And these spins are pointing along z direction, right? Because this is pointing up. Up means the component of the sz component of the total spin vector is plus half, and for the down state, this is sz component is along the minus z axis, right? And you can see that although sz operator preserves the spin, but Sx and Sy flips the spin orientation. It flips the up to down and down to up with different coefficients. Sometimes h by 2, sometimes plus minus h by 2, but they flip the spin, right? That's a very important point to remember. And I think this ends the discussion of spin angular momentum of a single electron. Please try to remember one important thing. Sometimes students confuse themselves, because I told you that for a single electron, S is always half, right? The quantum number S, that is always half, and ms could be plus half or minus half. That's for a single electron. But if you consider a multi-electron picture where you need to add the spin angular momentums, then this spin could be 1. That's not a problem. But don't confuse. When you see S is not equal to half for electrons, then you have to understand that's a multi-electron system, right? And then your things are complicated. But my discussion is limited to a single electron. These are the set of algebra you need to understand or remember to handle the problem of magnetism in a quantum mechanical setup, right? And I think that's about it on spin angular momentum. In the next lecture, I will introduce the concept of the total angular momentum, the J operator, right, where J is the L plus S. And for this lecture, that's about it, and thanks for listening.